One of the most frustrating things about being an electrical engineer is that we deal with invisible problems, and these can be really frustrating to track down and solve. Let's say, for example, I'm trying to read a push button with my microcontroller. When I press the button, my microcontroller reads 5 presses. Why is that? That's exactly the type of invisible problem that an oscilloscope can help you catch and fix. Before diving into this video, let's talk about why you would actually need an oscilloscope. If you work on electronics, chances are you own a digital multimeter like this. These are really useful for voltages that stay constant and don't change over time. But sometimes the signals that we want to measure aren't going to hold still for us. They're kind of like a toddler taking a family photo. That's where oscilloscopes come into play. They are great at visualizing voltages that change over time. So if you need to measure a voltage that's constant, you're probably going to want to use a multimeter, but if your voltage is changing over time, that's when you're going to want to move to an oscilloscope. Not all oscilloscopes are created equal. If you're looking to buy an oscilloscope or you just want to understand the one you already own, there are 3 key features that you want to know. First is the number of channels. That's just the number of signals that the oscilloscope can measure at once. The second feature that differentiates oscilloscopes is bandwidth. The bandwidth rating of an oscilloscope is simply the maximum frequency that it can reproduce faithfully. As a rule of thumb, you want to get a scope that has about 3 to 5 times the bandwidth as the highest frequency you're going to measure. So for example, if you want to measure a 25 megahertz signal, you'll need a scope with a 100 megahertz bandwidth. And finally, the last feature is the sample rate. The sample rate is simply telling us how many times per second the oscilloscope is measuring the signal and digitizing it. A similar rule of thumb applies for sample rate as well. Your scope will need a minimum of 2 times the sample rate of your highest frequency. But in practice, it's much better to have a sample rate of 5 to 10 times the frequency of your signal. If you want to understand this a little bit better, you can research the Nyquist theorem. In short, having more oscilloscope channels lets you measure more signals at once. A higher bandwidth lets you measure higher frequencies, and a higher sampling rate lets you digitize those signals a lot more clearly. If you're looking to get your first oscilloscope, you don't need to go crazy on those features. Quite honestly, a 2-channel, 50 megahertz scope with a 1 gigasample per second sampling rate is more than enough. There are a lot of great beginner scopes on the market that fall within that range. I happen to have the Rigol DS1054Z. It's actually a great scope for its price point. It's got 4 channels, so you can measure up to 4 signals simultaneously. It's got a 50 megahertz bandwidth, although that's upgradable with a key, and it has a sampling rate of 1 gigasamples per second. At first glance, this front panel might look a little overwhelming. It kind of looks like a spaceship control panel with all the buttons, but once you kind of break this down, it's not so bad. You can divide the knobs and the buttons into 3 categories. Buttons and knobs that control the horizontal display, buttons and knobs that control the vertical display, and buttons and knobs that control how you trigger the signal. Let's start simple. I'm going to measure the 1 kilohertz square wave that is present on the front panel of the oscilloscope. Most scopes have this for testing and calibration purposes. The most simple way to start measuring on an oscilloscope is to hit the auto button. This automatically adjusts both the vertical and the horizontal scale. So let's see how the scope adjusted for this signal. If I look down here, I can see that my vertical resolution is 500 millivolts per division. So that just means that every horizontal grid line going across the screen is 500 millivolts. So I'm going to look for the ground reference down here, and I'll count the divisions and see what voltage this square wave is. So we have 500, 1000, 1500, 2000, 2500, and 3000 millivolts. So that is a 3-volt square wave. On this scope, all of the vertical controls are outlined here in this area, and I can adjust the vertical resolution by turning this knob, and you'll see this number change down here. So now it is 1 volt per division. Our 1 kilohertz signal hasn't changed. It's still 3 volts, but our resolution has changed. We count 1, 2, 3 horizontal lines, and that's how we know our square wave is 3 volts. So depending on the voltage of your signal, you'll want to adjust the vertical resolution to capture that whole signal. If you're measuring a 12 volt or 24 volt signal, you'll want to make sure that that all fits within the real estate of your screen. And now I'm going to move on to horizontal controls. On this scope, the horizontal controls are outlined here in this gray area. And I can change the horizontal resolution by turning this knob. We start out at 200 microseconds per division. So let's go ahead and count the vertical grid lines from rising edge to rising edge. That will tell us the frequency of our signal. I'll start with this rising edge here because it lines up with one of our vertical grid lines. So we've got 200, 400, 600, 800, and 1,000 microseconds. So that's 1 millisecond, and that makes sense because I know that this is a 1 kilohertz square wave. If I want to change the horizontal resolution, all I do is turn this knob here, and now it's 500 microseconds per division. So this is how you adjust the vertical and horizontal resolution depending on what your signal looks like. A great way to start is hitting the auto button and then fine-tuning and adjusting from there. And finally, we'll move on to the trigger control section. Adjusting the trigger settings will help you achieve a stable signal on your oscilloscope. The first thing to check is to see which channel your trigger is set to. In my case, I have the probe plugged into channel 1, and so that is what I have here on the source. So you can trigger on a whole bunch of different things, but as you're starting out, you'll probably just want to stick with triggering to a rising or falling edge. And then I will select what type of edge by clicking this button. I can select rising edge, falling edge, or any change in edge. If I select rising edge, that will put the rising edge of my square wave right in the middle of our display. If I want that rising edge to move left or right, I can simply change the horizontal position by changing this knob here. If I want to reset it back to the middle, all I have to do is press that button in, and it centers it right back to the middle. The next setting you're going to want to know how to use is the trigger voltage. That's this knob here. So I know that I have a 3-volt square wave, and I'm looking for a rising edge. So I'm going to pick a voltage that's between 0 volts and 3 volts to trigger on. So I'm just going to pick something in the middle like 1.5 volts because I know I have a nice clean square wave. And that's basically it. There's really only 3 types of controls on an oscilloscope: vertical controls, horizontal controls, and triggering controls. So yeah, it might look like a spaceship control panel at first, but once you break it down into vertical, horizontal, and triggering controls, it starts to make a lot more sense. Now that you're armed with this knowledge, let's try a real-world example. Earlier, I had this push button in my project and I was reading it with a microcontroller, but every time I pressed the button, the microcontroller would read a whole bunch of button presses. And the reason is because mechanical switches like this don't make a clean contact when you press them. It's kind of like when you drop a bouncy ball, it'll make several bounces before making full contact and staying closed. So let's connect it up to the breadboard. I'm going to connect one end to ground, and the other end I'm going to pull up to 12 volts using a 10K resistor. Now that I've got the push button connected to the breadboard, let's measure it using the oscilloscope. I've connected my USB-C breadboard power supply that I built in a previous video, and I've set it to 12 volts. So let's see if we can see that on the oscilloscope. Channel 1 should just be reading a constant 12 volts because it's being pulled up by the resistor. So I'm going to hit auto and see what the scope does. And you know what? It didn't do a good job. It set the vertical resolution to 20 millivolts per division. Let's adjust that to 5 volts per division using the knob. And then I'm going to center that by pressing the button. Right now, the scope is reading a constant 12 volts, but as I press it down, it reads a constant 0 volts. Then when I let it go, it goes back to 12 volts. But I'm interested in the transition between 12 volts and ground. And so I'm going to be looking for a falling edge. Remember earlier when we talked about the trigger controls? I need to set those to trigger on the falling edge. And now that I have that set, I'm going to put the scope into single capture mode by pressing that button. So when I press the button, we should see the falling edge. Okay, so I've got a problem. It's not triggering, but I just noticed that my trigger voltage level is set to 24 volts. If I have a 12 volt signal being connected to ground, the oscilloscope is never gonna find a falling edge that is at 24 volts. So let's go ahead and fix that problem by bringing this triggering voltage down below 12 volts to 6 volts. The scope is still in single capture mode, and I'm gonna press the button, and there we go. We've got a falling edge. And as I described, we've got bouncing going on because this is a mechanical switch. It looks like it's still bouncing beyond the edge of my screen, so I need to adjust the horizontal resolution so that I can see everything. Now I've got my horizontal resolution to 1 millisecond per division. So that means every vertical line is 1 millisecond. Let's see what our switch bounce looks like. There we go. So we can see that it happens for about 1.5 milliseconds, and then it finally settles down to ground. So that explains why my microcontroller was reading multiple button presses. That's because it's finding all of those edges. So what is the solution to this problem? We need to add some sort of low-pass filter. So I'm actually going to use the low-pass filter calculator on DigiKey's website. I can enter my resistance and my capacitance, and it will tell me the cutoff frequency. So if I enter 10K and 0.01 microfarad, that tells me my cutoff frequency is around 1600 hertz. Anything faster than that will get attenuated. So let's go ahead and wire that up on the breadboard. And now I can take advantage of having more than one channel to measure with the filter and without the filter. Okay, so the blue signal now is that filtered signal, and I can see that it's doing something. It is slowing down those high frequency pulses, but by the look of this, it's not enough. So let's change the value of our capacitor to 0.1 microfarad and see what that does. All right, I'm ready to trigger again, and we'll see how this looks. All right, that looks so much better. You can see how the low pass filter really attenuated those high frequency signals, and it really smoothed it out. And now we get one kind of continuous falling edge, and that should be much better for the microcontroller to read. Let's say I have a couple of different measurements that I want to compare. The cool thing about oscilloscopes is that you can actually save screenshots to a flash drive. So let me plug that into the USB port here, and now I can hit the print button, and it's capturing a PNG file to the flash drive. And I can take that into my computer, I can write a report, I can compare, and do all sorts of things. And that's not the end of it. Oscilloscopes have a ton of other features that I haven't talked about yet. For example, this oscilloscope has a USB port in the back. This allows me to connect it to my computer, and I can run software to control the oscilloscope. It also has an Ethernet jack in the back, so you can connect it to your network and do remote monitoring and testing and configuration and all that kind of stuff. Some oscilloscopes even come with the ability to analyze logic signals. So if you have SPI or I2C signals, you can measure them and decode them right on your oscilloscope. So why is an oscilloscope such a valuable tool in your workshop? Because it lets you see what your circuit is actually doing instead of what you expect it to do. Whether you're chasing down a glitch, verifying timing, or just learning how your signal behaves, this tool can give you insight that no other tool can. Although an oscilloscope might look complex at first, once you get the hang of it, it can become the most powerful tool in your toolkit. I know I left out a ton of information about oscilloscopes in this video. So if you want to learn more about these, or if you have questions, let me know down in the comments, and maybe I'll make a part 2 to this video. My name is Zach, and I'm the Byte Size Engineer. Thanks for watching.